right? So I want to somehow, and so this seems to be intuitively kind of what I want to do. If you're doing a divide and conquer in clustering, you want to split things into roughly equal size. And so if either of these volumes is too small, then 1 over the volume is going to shoot up pretty quickly. You want them both to be as small as possible, otherwise, otherwise this term will be too large. And you also have this cut. You don't want the cut to be too big. You could also split them into equal. If you just looked at the volumes to be well split, well then you're actually better off kind of doing something that cuts a lot of edges, something like going across here, but then the cut becomes too large. So you want to have both of these terms. Okay, so now I want to find a good normalized cut. But if the graph is small, it looks like this should be easy. You can just kind of look at it and do it and write down the normalized cut, say that's small, that's good, and you're happy with yourself. But if you want to do this in general, we want kind of some neat algorithmic trick to do this. And so we're going to use this graph representation and eventually take the eigenvalue of some graph, and that's why it's called spectral clustering. Eigenvalues are like a spectral method. So let's let me erase this. I don't have an eraser. All right. Those are chalk erasers. I think that would just cause more damage. Okay, these drawers are useless. What do I have here? Survival analysis. Well, that actually sounds like it might be useful. Okay, all right. So I want to somehow turn this graph into a matrix, and so I have this representation of the matrix, and I'm going to start with this one, right? So I'm going to start with a matrix A, which is going to be it is going to be exactly this representation, where it was 0, 1. And so I call this A because this was known as the adjacency matrix. Okay, so it's kind of capturing which node is adjacent to another node, right? That's exactly what's going on here. So if I thought of this as, if I look at this representation here, I have node A is adjacent to node B, and so you can see A and B are adjacent, they have an edge between them. So I have a 1 there, right? So that's what this adjacency matrix is capturing. I'm also going to have another matrix, which is going to be called the degree matrix. Okay, and so the degree matrix is going to have special structure in that it's going to have all zeros except for the elements that are on the diagonal here. So this part is all 0, this is all zeros, but what's on the diagonal is the degree of that element. So before I had this, the first row and the first column corresponded to node A. Now this tells me how many edges does node A have. So node A has 3 edges, right? If I look at the graph, A has 3 edges, it connects to C, D, and B. B has 2 edges, so B is going to get a 2. C has 3 edges again. D has 3 edges. E has 3 edges. F has 3. G has 2, and H has 1. Right? So on the diagonal, I just write down what is the degree. And in fact, if I went and I looked at the A matrix, I can just sum up all of the ones along here. So if you were to, we'll talk about, some point we'll generalize this adjacency matrix towards the end of the lecture, and you can generalize this by just adding up the sum of the elements along each row or column, and that will get you the degree. So now I have this A and this B matrix, and so then I need to do one more trick. Well, I'll start out with, you can get this other matrix, which is called the Laplacian matrix, which is the degree matrix minus the adjacency matrix. So, and this is sometimes useful, and we'll come back to this one in a second. But for the normalized cut, it turns out what you want to use is what's called the normalized Laplacian. And this is a bit more complicated. This is the identity matrix minus d to the minus 1/2 times a times d to the minus 1/2. Okay, so I'll go through an example in a minute here. So you can calculate this Laplacian matrix, and now, this Laplacian matrix has the same information in it as the adjacency matrix, or this normalized Laplacian. And so then in order to get the, so here's, this is the, so this is the adjacency matrix, this is this is the degree matrix, and you will actually talk about this d to the minus 1/2. This should be d to the minus 1/2. And so there, well, what this means, so if you're taking like a value to a power, you understand what this means. If you take a matrix to a power, well, if this is a positive number and it's an integer, well, we'll talk about what that means later. Later on in the class when we talk about Markov chains and stuff. You can do something else if this is a diagonal matrix. That's pretty simple to do. You just take every element that's along the diagonal and you apply this power to it. So the degree matrix, so if I look here, this degree matrix had 3 in the first element, and now I have this 3 to the minus 1/2. So I'm basically taking 1 over the square root of 3, and I get 0.577 or so. And this is, I had 2, so this is 1 over the square root of 2, 0.707. Right? And so that's what this should be d to the minus 1/2. That's what this matrix represents. And then this is the normalized Laplacian matrix. So, so it's still going to have zeros where the adjacency matrix and where both the adjacency matrix and the diagonal matrix had zeros, it'll still have zeros, right? It's only going to have information where I had edges, as it turns out. And it's going to have the property that, basically why this is called normalized is that if I took out the part that's on the diagonal here, which is going to be all ones, then see how does this work? And I think if I so this is not the part there's going to be, I think there's some way where this is normalized, so I forget where that is. Okay, so the next step, once you have this normalized Laplacian matrix, is you're going to call an eigenvalue decomposition, which is some matrix technique you can do, which basically finds the most important direction. So has someone not heard of an eigenvalue or an eigenvector before? Okay, so if you have a matrix M, okay, so an eigenvector is one such that you can multiply this matrix times a vector M, and it's going to be equal to some scalar value times this vector. Okay, and so you could then create, so this scalar value is always 1 if you wanted to. So then, what if this scalar value lambda? So this is a matrix. And so this lambda is a scalar. So that means if I multiply the matrix by this vector, I get back the same vector. Okay, maybe I've scaled it, but if I have scaled up the vector, then I can multiply by the vector and get back the same vector. Typically what you want to do is have, so the vector is actually a unit vector, and then this becomes an interesting quantity. So now, if you have this property, which seems kind of magical, then this vector here is what's called this is called an eigenvector, and then the scalar is what's called the eigenvalue. Okay, and so if you take the eigenvalue of the Laplacian, what's going to happen is the number of distinct or at least the interesting ones of the eigenvalues and eigenvectors you get is going to look like this. And the eigenvalues, you will get them returned if you call this in MATLAB. So they're in sorted order where the smallest ones come first. And the smallest ones are the most important ones. And they each correspond with the vector here, which is each of these vectors is going to be a unit vector. Okay? So this is a unit vector, this is an eigenvector, and this is the associated eigenvalue. And all the eigenvectors are going to be orthogonal to each other. This will be the choice of the eigenvector with the smallest value here, and then this will be the smallest value given that it's going to be orthogonal to this one. So orthogonal means that they point in opposite directions, or not, if you took the dot product of 0 in any high-dimensional space here. Okay, so, it's not totally needed to understand exactly what the eigenvalue decomposition of a matrix is, but it's going to be really useful for our algorithm. We'll talk about how to use this. And so what's going on is the first eigenvector right here, which is this first column, is going to be really useful. Okay, so now what happens is this first row corresponds with element A, right? So this was the Laplacian we constructed from our adjacency matrix and this degree matrix, which was based on this graph. So the first row corresponds with A, the second row corresponds with B, third row C, and the fourth row D, right, and so on. So if you look at this first eigenvector, what's interesting about it?
Positive with all the ones it touches.
So you say it's positive.
Well, so like A, B, C, and D on this row.
Yeah.
If you said A is this way, then B is this way, then A and B and C and D are all positive, and they're all connected for the most part.
Yeah. So what's interesting? Yeah. So I think you're basically onto it. So the first four are all positive, and the next four are all negative. And that also corresponds with how we want to split the cluster. All the positive ones are in set S, all the negative ones are in set T. And this is not an accident, right? This is kind of something cool that's going on. It's not, you don't always want to just pick them positive and negative, but it's kind of telling you how to align these things based on So based on these values. All right, so let me show kind of a picture here. So let's say if I actually were to write out these values in the sorted order based on this eigenvector. So things go from about minus, well, let's go, so this would be minus 0.5, and this would be plus 0.5. So I'm going to say that if I put them on this line, then A, and so this is going to be 0. So A is going to be about here. This is 0.38. B is going to be pretty close here. Let's see, C is going to be around here. D is actually going to be in the same location as A, and this is not by accident. I look at E. E is about here. Let's see, then F is going to be out here. G is going to be, say G is here and H is here. Okay, so I've kind of drawn these, I've taken this data and I've put it now in this one-dimensional space. And so once I've done this in this one-dimensional space, then I can just take my cut and say the positive ones are in one cluster and the negative ones are in the other cluster. And so just doing this gives you a fairly good clustering based on the normalized cut. Okay, so now what you might think is that H may actually be a little bit further, you may want it to be further out. Why is H closer to these than say, F? So the reason is a little strange, and it's hard to see in this small example, but it could be that, you know, there's a very tight cluster here that was pretty large, and H was kind of hanging out on its own. And I wanted to kind of balance the two sides. So instead of picking F to balance to pull over here, it's better off pulling something like H. It turns out it's even better to pull over E because it's actually connected to these. But H is a bit better because it doesn't have too many edges to it. So if you use just the unnormalized Laplacian, D minus A, it's actually going to spread them out a little bit better, not worrying about the normalized cut as much. So a different way of doing this. So, yeah, okay. So maybe this is a good point to kind of go through how this works in MATLAB. And so if you haven't used MATLAB or you don't have a license, what I'm actually using is Octave, which is an open source free version. I think it's open source. It's a free version of something that works like MATLAB. It's a little buggy in some places. Doesn't work quite as well, but you don't have to worry about a license or anything like that. And for everything we do, Octave will work fine. So, yeah.
You can also SSH into K or any
Yeah.
U account.
Yeah, so if you don't want to SSH in or you're offline, you can download Octave and use that as well. Right, so I have my matrix A in here. This is my adjacency matrix, which I wrote up. And so I have my degree matrix, and I also worked out the degree matrix once I've taken it to the -1. Right? So now if I want to write out the Laplacian, or the normalized Laplacian, I get this. And actually you can write this as, so this is an identity matrix of size 8, and a DH times A times H. All right, so this is how I got my normalized Laplacian. And if you see, you know, remember these things were all zeros, and there's some rounding error that's pretty small. It only, if I wrote out for more precision, it'd still be a lot more zeros, but it's not exactly zeros in there. But that's not going to matter so much. You can kind of, sometimes if you're working with these things and you do stuff, you'll actually take things which are close enough to zero and round them down. If you want to store it more in a more compressed form. So this is my Laplacian matrix, and then I can do, let's see, my normalized Laplacian. I do this, and I get the eigenvectors and the eigenvalues. And so this one is basically 0. It's something times e to the minus 17. So the first eigenvector or eigenvalue is basically 0. The second one here is about 0.125. Right? And so the first eigenvector is pretty meaningless. The second eigenvector is really interesting. Right? This is what we are using in order to spread these points out and kind of get them on the line. Okay, so this kind of may seem mysterious how this works, but these are very standard commands how to use. And how you actually calculate the eigenvalues and eigenvectors, you know, there's actually a long history of how to do this, and there are methods and there are other ones that are more stable and have better rounding errors, and MATLAB or Octave will all take care of this for you. We'll talk a little bit later about some newer ways to do this at larger scales if you are okay with some various errors in different places. Okay, so I've got this first eigenvector here, and then also this second eigenvector. And this was once you're in MATLAB or Octave, very easy to compute, and it can work up to fairly reasonable size scales, like hundreds by hundreds. It should still work. If you get up to thousands and thousands of points, then there are other techniques you'll want to use, and I'll mention some of these later in class. Okay, so now, so I mentioned that, so now if I drew these, so this is again a different drawing of the same graph, and this is the first eigenvector here. This is V1, and now I've scaled them by the by 1 over the square root of the eigenvalue. Okay, it turns out that's what you want to scale them by. And then I've also drawn a second dimension here. This is the second eigenvector in the y direction here, also scaled by 1 over the square root of the eigenvector. So if I remember, if I look back up here, this was 0.125, this is 0.725, right? So these are off by, if I take the square root, but they're off by kind of a factor 2 or 3, something like that. So the first coordinate is scaled much more than the second coordinate. Okay, so you can think of, and you can actually do this for even more coordinates too. You can kind of embed them in some three-dimensional space by using the first 3 eigenvectors. And so this is kind of what a lot of these, if you've heard of these manifold learning or these nonlinear dimensionality reductions, where you're trying to do this, a lot of them are based on something kind of like this. There are other techniques, but this is a fairly general technique. You have a graph of data, and then you can embed it into some k-dimensional space by using the first k eigenvectors and eigenvalues of the Laplacian. And this works pretty well. I've kind of transformed the points in a way where I've tried to preserve the spatial similarity between the points based on how their edges are connected. Okay, I flipped this here in this drawing here. I've got the positive ones in the general positive direction, so that's why it'll be kind of like a mirror image here. Okay, so now if I wanted to do a clustering, the simplest thing to do is you just split on the first eigenvector, based on the positive ones on one side and the negative ones on the other side. You could then say, then look at the two subgraphs, look at subgraph S, look at subgraph T, and then redo the same thing on just these subgraphs. Pump both of these back in, create the adjacency matrix and the degree matrix, now ignoring this edge which goes between them, and then create the normalized Laplacian and, you know, repeat this process. But that's kind of a little expensive, and I mean, so you can, if you worked out the math, it's just kind of more complicated to do. Another way, which is a little bit simpler, is to actually just look at, say, if you wanted to get into 4 subgraphs, look at the first 2 singular, or the first 2 eigenvectors here, and then split based on these. So C is in one cluster by itself. B, A, and D, which are A and D are on top of each other, are in another one. G and E are in one, and F and H are in one. Okay, and so by looking at the first 2 eigenvectors, I automatically get these 4 clusters. I don't have to repeat this process over. And this may not be the best thing to do, but it's pretty easy to do. So this is one way to do it. So another thing to kind of, so another important thing is that our goal, again, is this normalized cut. This is really the function that we want to optimize. And so it often works well to split on 0. You know, if you're not want to do any extra work, you can do that. But you're given all these points in this sorted order. And basically, by one more pass of the data, you can scan through these points, and you can maintain these 2 quantities, the cut score and the volume score, as you're scanning over this data in sort of order. And sometimes, instead of something that looks like this, where you have 0 here, what you're going to get is a bunch of points, say, here, and then you're going to get this gap, and you're going to get a bunch of these other points. And so because these points are really close to each other, you then, sometimes it's better to have a normalized cut that's maybe not exactly at 0. You may want to choose some value a little bit greater or a little bit less than 0, and it may give you a better normalized cut score. And so you can kind of scan over those and do a little bit better that way.
Will this algorithm ever give you a subgraph where not all the nodes are connected? They used to be connected, like whatever. Maybe give you ABD and then H. I mean, this one wouldn't.
Yeah.
And it's obvious that in this case it wouldn't, but.
Well, so sometimes strangely, sometimes you actually want to do that. So it could be that I'll have something, like if I had a different graph that looked like A, B, C, and then I had E, F, G, oh, I forgot D, okay. And there's one edge here, these is actually a clique, so these are all connected. And then I have H. Or it may be that there are even more nodes here. What you'll want to do is actually to put this in one cluster, and then everything else is T. And so you'll actually want to bring H into this set, and this will be a better normalized cut. If you have a really dense cluster, which is roughly half of your nodes, or half of your edges are in here, you're better off making this one cluster and kind of have these hanging off things, even though there's an edge connecting here, grouping it with everything else. And so that's kind of what's going on. That's why H is further this way than if I had laid it out.
Okay. So it could get a subcluster that's not connected, even given a graph that's fully connected.
Yeah, so that can happen. And for normalized cut, that's sometimes what you want. You'd rather, instead of having H be part of here, where it's not really part of this cluster, it just happens to have this one edge here. It's only one edge, right? And in a really large data set, one edge is not that important. You're going to throw it in, and then the next set, it'll probably be, you know, what's more likely is that you actually have H here, and then you also have you also have say, I here. You have these whole bunch of stuff hanging off you. And you'll have this and all these in one cluster. And then in the next level down, you'll split these off in one way and these all in another. And that'll actually make more sense. Sometimes you're pulling something out of the middle instead of kind of splitting in two in that way. And so this kind of normalized Laplacian will actually, it'll kind of sort things in the right way. If the graph looked like this, it'll probably pull I and J and H over here, and they may actually have this, I guess, a negative, they may have a negative value, but then E, F, G, and D would be a much more negative, and it'd be a situation like this, where you may not cut at zero. And it will give you a better normalized custom. All right, so let me show you some other pictures here. So if instead of the Laplacian, the normalized Laplacian, I did the regular Laplacian or the unnormalized Laplacian. And if you look up literature in Wikipedia and other sources, different people call the Laplacian to be slightly different things. But I think the most common is, there's some literature, some of the early literature on spectral clustering called the normalized Laplacian just the Laplacian. But generally, this is the Laplacian, which is just V minus A. And so this Laplacian has some other neat properties here. So if you look at this, it has the property that every row and every column has its sums to zero. If I added up all the elements, it's going to be zero. Right? That was because the degree matrix was adding up all of the ones in the adjacency matrix, and now I'm subtracting off the adjacency matrix. So this makes sense that it's doing that. It's going to kind of have this neat interpretation where you can think of, if you look at every row, you can think of like water flowing into a node based on these negative values, and that's flowing out of it based on this positive value. There's kind of some conservation of the flow of the water here. And there's some ideas that will come back to something similar when we talk about when we talk about Markov chains, which will be kind of a very different way to think about graphs. You'll kind of get some similar intuition with these probability transition matrices. So the other kind of neat things I mentioned, there's different ways you can get this layout. So you can also take the eigenvalue decomposition of the unnormalized Laplacian, and you're going to get these, get something else that looks useful. The second eigenvector now is, in this case, is called the Fiedler vector, and is used in a lot of similar applications for the spectral clustering. And now the layout, if I drew it before, looks like this. Okay, so what might be nicer about this, if I just looked at the first coordinate, is now this node H got spread out further to the right. I separated them in a way that if I were trying to draw these so they best fit on a straight line, then the unnormalized Laplacian actually does a better job. It's not trying to kind of do this normalized cut. It's trying to put all the graph onto a single one-dimensional coordinate system. So here, now H should be spread out on the edges. Instead of being on the inside, it's here. So if I were to draw this one here, what I'm going to get instead is you're going to get B out here, and then essentially A and D, and then C, and then E, and then G, and H, right? So I'm kind of, if I spread these out, they're going to kind of look, so they're going to kind of look something like this, where C and E are closest across here, where I still have that, but then H is spread out at the end, and that's kind of what's going on with this drawing. So the unnormalized Laplacian does a better job of kind of squashing into one dimension, Whereas the normalized one works better for the normalized cut score. Okay, so what is another interesting thing? So why did A and D both wind up in the same exact location in both the normalized layout and also in the unnormalized and also the normalized way? So the unnormalized, they're both also right here, right next to each other.
Same number of degrees?
Yeah, that's part of it, but there are a lot of things that have the same number of degrees. Like there were 5 things that had degree 3. Yeah, so they're perfectly symmetric, right? So if they're both connected to each other, they're both connected to B, and they're both connected to C, and not connected to anything else. From the perspective of a graph, there's no difference between them, right? When I drew them like this, you think, okay, there's some sort of embedding where A and D are in different positions. But that's just to draw them. Once I write it as a graph, if I swap them, if I swap the value of A and D in every one of the edges, then the graph wouldn't change. And since this algorithm only looks at the graph structure, it has no way of distinguishing them. So it gives them both the same value for the eigenvector. And so you aren't able to distinguish them in either of these rungs. They're the exact same value. If you look at the actual eigenvector decomposition, so A and D here, they're both the same for the first, the second one, the third one. Finally, on the fourth one, there's this weird column here, which is saying it's all zeros except for A and D, and then it has to be a unit vector, so they're both 1 over the square root of 2. But one is negative, one's positive. Right, so what's happened here is, at some point I had to kind of differentiate these to create an orthogonal basis. And this was kind of the point where there's no more information really in my graph. There's some other stuff going on here, but probably what happened is that